A human body exposed to the vacuum of space remains conscious for approximately 9 to 12 seconds. This number isn't theoretical. It comes from documented depressurization incidents, animal studies conducted in vacuum chambers during the early space program, and measurements of how rapidly oxygen stored in the bloodstream depletes when breathing stops. In 1965, a technician at the Johnson Space Center experienced accidental depressurization in a vacuum chamber during a spacesuit test. He remained conscious for about 14 seconds before losing awareness and survived with no permanent injury after the chamber was repressurized approximately 30 seconds later. That event, combined with controlled animal experiments conducted by NASA in the 1960s and physiological models of human oxygen consumption, gives us a precise starting point. The clock begins the instant pressure drops, and the body's limits are measured in seconds, not minutes. If you find this kind of evidence-based exploration interesting, engaging with the content helps similar material reach audiences who value scientific precision over speculation. The question of survival in deep space isn't a single question. It's a cascade of physiological limits, each triggered at different timescales, each constrained by measured properties of human tissue, blood chemistry, thermal conductivity, and radiation absorption. Understanding maximum survival time requires breaking down what deep space actually means in physical terms, and what survival means when applied to biological systems operating outside every condition they evolved to tolerate. Deep space, for our purposes, is defined as the environment beyond Earth's protective magnetosphere and atmosphere, far from any planetary body that could provide heat, pressure, or shielding. The physical characteristics are measured and consistent. Near-perfect vacuum with pressure effectively zero, temperature determined only by radiative heat exchange with an average background of 2.7 Kelvin, exposure to solar and cosmic radiation without atmospheric filtration, and no breathable gas. These aren't dramatic descriptions. They're baseline environmental parameters that have been measured by every spacecraft that has operated beyond low Earth orbit, from the Apollo missions to Voyager probes to the Mars Science Laboratory during its cruise phase. The human body maintains life through continuous regulation of pressure, temperature, oxygen delivery, and cellular protection from radiation. Each of these systems has a failure point, and those failure points have been studied through decompression accidents, high-altitude exposure incidents, thermal tolerance experiments, and radiation biology research spanning decades. The maximum survival time is determined not by the slowest failure, but by the fastest one that causes irreversible damage to critical organs, particularly the brain. Let's start with pressure, because it fails first and its effects cascade most rapidly. Human tissues and fluids exist under approximately 1 atmosphere of pressure at sea level, roughly 101.3 kilopascals or 14.7 pounds per square inch. This pressure keeps gases dissolved in blood, maintains the integrity of cell membranes, prevents bodily fluids from vaporizing, and allows the respiratory system to function. The vacuum of space offers essentially zero external pressure. Measurements from spacecraft instruments show pressure levels below 1/1,000,000th of an atmosphere in most regions of space. When a human body transitions instantly from 1 atmosphere to 0, several things happen simultaneously, and the timeline of each is constrained by physics and measured biological responses. The most immediate effect is not explosive decompression in the Hollywood sense. The body doesn't rupture or explode outward in a dramatic fashion. Human skin and connective tissue are strong enough to contain internal pressure even against a hard vacuum. This has been demonstrated in vacuum chamber tests with animal subjects and is consistent with the tensile strength of human tissue, which can withstand pressure differentials of several atmospheres. The skin acts as a pressure vessel, maintaining structural integrity even as internal and external pressure diverge dramatically. What does happen, however, is rapid depressurization of the lungs and respiratory system, and this is where the first critical damage can occur. If a person attempts to hold their breath during sudden decompression, a natural instinct when facing danger, the air in their lungs expands according to Boyle's law, which states that pressure and volume are inversely proportional at constant temperature. The mathematical relationship is simple. PV equals P2V2. Lung volume at normal pressure and full inspiration is about 6 liters. If external pressure drops from 1 atmosphere to near 0 while the airway is closed, that's 6 liters of gas attempts to expand without limit. In practice, the expansion is constrained by the chest cavity and lung tissue itself, but the pressure differential creates enormous stress on the alveolar walls. The result is barotrauma, overpressure damage to lung tissue. This can cause alveolar rupture, where the tiny air sacs in the lungs tear open. When alveoli rupture, air escapes into the pleural space between the lung and chest wall, causing pneumothorax, or collapsed lung. More dangerously, air can enter the pulmonary capillaries directly, creating arterial gas embolism. These gas bubbles then travel through the bloodstream, potentially blocking blood vessels in the brain, heart, or other vital organs. Arterial gas embolism is immediately life-threatening and can cause stroke-like symptoms, cardiac arrhythmias, or death within minutes. These injuries have been documented extensively in rapid ascent diving accidents, where divers holding their breath during ascent experience similar pressure differentials, though typically much smaller than the full atmosphere-to-vacuum transition. Medical literature contains numerous case studies of divers who suffered pulmonary barotrauma during ascents of only 10 to 20 meters, representing pressure changes of 1 or 2 atmospheres. The atmosphere-to-vacuum transition is far more severe, and holding the breath during such decompression would almost certainly cause severe pulmonary injury. The correct response, and this is emphasized repeatedly in astronaut training protocols, is to exhale immediately and continuously during depressurization. This allows lung gases to escape harmlessly through the mouth and nose without causing rupture. Assuming that response is followed, and trained astronauts would likely follow it reflexively, the lungs deflate safely as pressure drops, and the immediate mechanical damage is avoided. However, this doesn't mean oxygen delivery continues. In fact, it guarantees that it stops immediately. Oxygen in the bloodstream comes from 2 sources: dissolved oxygen in plasma and oxygen bound to hemoglobin molecules in red blood cells. Under normal conditions at sea level, arterial blood leaving the lungs is about 97 to 99% saturated with oxygen, meaning nearly all available hemoglobin binding sites are occupied. Venous blood returning from tissues is about 70 to 75% saturated, having released oxygen to cells for metabolism. The difference represents the oxygen extraction that occurred in the capillaries of tissues throughout the body. The brain is the most oxygen-dependent organ in the body. It consumes roughly 20% of the body's total oxygen supply despite representing only about 2% of body mass. A typical adult brain weighing approximately 1,400 grams consumes about 3.5 milliliters of oxygen per 100 grams of tissue per minute under resting conditions. This translates to roughly 49 milliliters of oxygen per minute for the entire brain, or approximately 0.8 milliliters per second. This consumption rate is constant and non-negotiable. Neurons cannot store oxygen for future use, and they cannot switch to anaerobic metabolism the way muscle cells can. Brain cells require continuous oxidative phosphorylation to produce ADP, the energy currency that powers all cellular functions. When breathing stops, the oxygen already circulating in the bloodstream continues to be delivered to tissues, including the brain, but no new oxygen enters the system. The rate of consumption remains constant, so the available oxygen depletes rapidly. The total oxygen reserve in the bloodstream at the moment of decompression can be calculated based on blood volume and oxygen saturation. An average adult has approximately 5 liters of blood. At normal oxygen saturation, this blood contains roughly 1 liter of oxygen when accounting for both dissolved oxygen and oxygen bound to hemoglobin. However, not all of this oxygen is available to the brain. Oxygen is distributed throughout the body based on blood flow, and while the brain receives about 15% of cardiac output under normal conditions, the entire oxygen reserve isn't instantly accessible to brain tissue. The practical oxygen reserve available to maintain consciousness is much smaller, approximately enough to sustain brain function for 10 to 15 seconds under resting conditions. Measurements from breath-hold diving research, medical studies of apnea, and the documented 1965 vacuum chamber incident all converge on the same range. Consciousness persists for 9 to 15 seconds after breathing stops and no new oxygen enters the system, depending on factors like activity level, metabolic rate, and initial oxygen saturation. Physical exertion increases oxygen consumption dramatically, up to 10 times resting levels for intense activity, which would reduce the consciousness period to as little as 5 to 7 seconds. Conversely, A person at complete rest with maximally oxygenated blood might extend consciousness to perhaps 18 to 20 seconds, though this is at the extreme upper limit. After this initial period, the brain enters hypoxic failure. The sequence is well documented from high-altitude studies, medical emergencies involving airway obstruction, and experimental hypoxia research. As oxygen partial pressure in arterial blood drops below critical thresholds, typically around 60 millimeters of mercury, compared to the normal 100 millimeters of mercury, cerebral function begins to deteriorate. Vision narrows as peripheral visual processing fails. Cognitive function becomes impaired, with slowed reaction times and confused thinking. Fine motor control deteriorates. Then, as oxygen levels continue to fall below 40 millimeters of mercury, consciousness is lost entirely. Unconsciousness occurs because neurons can no longer maintain the electrical gradients necessary for signaling. Every neuron maintains a resting potential of about -70 millivolts across its cell membrane, achieved by actively pumping sodium ions out and potassium ions and using ADP-dependent ion pumps. When ADP production ceases due to oxygen deprivation, these pumps fail. The ionic gradients dissipate, membrane potential collapses, and neurons can no longer generate or propagate action potentials. The brain, from an electrical standpoint, goes quiet. This process is identical to hypoxia at extreme altitude or during drowning. The mechanism is the same, involving oxygen depletion and ADP exhaustion. The only difference in space is the speed, because no new oxygen is entering the system and because the depressurization itself may reduce oxygen partial pressure in the lungs even further, accelerating the washout of remaining gas from the respiratory system. Unconsciousness, critically, does not mean immediate death. The heart continues to beat, driven by its intrinsic pacemaker cells in the sinoatrial node, which have their own oxygen reserves and continue functioning for a period even without fresh oxygen supply. Cardiac function can persist for 1 to 2 minutes after consciousness is lost. If repressurization and oxygen delivery are restored within this window, roughly 90 seconds to 2 minutes total from the initial decompression, survival without permanent brain damage is possible. This is directly supported by the Johnson Space Center incident, where the subject was unconscious for approximately 15 to 20 seconds and experienced no lasting neurological effects after repressurization. Animal studies conducted during early space program research support this timeline. Chimpanzees and dogs exposed to vacuum conditions in controlled experiments lost consciousness within 10 to 15 seconds and recovered fully when repressurized within 90 seconds. These experiments, while ethically problematic by modern standards, provided crucial data on mammalian responses to vacuum that have informed every subsequent safety protocol in human spaceflight. Beyond 2 minutes of hypoxia, brain cells begin to die due to ADP depletion and the subsequent failure of ion homeostasis. Without ADP, neurons cannot maintain their membrane potential, as mentioned, but they also cannot prevent calcium influx. Calcium ions flood into cells, triggering enzymatic cascades that break down cellular structures. Mitochondria swell and rupture. DNA fragmentizes. Cell membranes lose integrity. This process, called excitotoxic cell death, causes irreversible damage. Even if oxygen delivery is restored and circulation resumes, dead neurons do not regenerate. The damage is permanent. The extent of damage depends on duration. At 2 to 3 minutes of hypoxia, damage begins but may be limited to specific vulnerable brain regions, particularly the hippocampus, which is involved in memory formation. Survival with some cognitive impairment is possible. At 4 to 5 minutes, damage becomes widespread, affecting the cortex and resulting in severe cognitive deficits. At 6 minutes or longer, the damage is catastrophic, often resulting in a persistent vegetative state even if the heart is restarted. Cardiac function itself begins to fail around 5 to 6 minutes of hypoxia, as cardiac muscle cells also deplete their energy reserves and lose contractile function. At 10 minutes, the heart has stopped, brain tissue is extensively necrotic, and resuscitation is effectively impossible. Even if heroic medical intervention manages to restart the heart and restore circulation, the neurological damage is so severe that meaningful recovery cannot occur. The person may survive in a purely biological sense, organs kept functioning by mechanical support, but the brain's higher functions, the structures that constitute consciousness and personality, are destroyed. Therefore, the maximum time a human can survive in deep space, defined as the point beyond which recovery of meaningful brain function is not possible, is approximately 10 minutes. This is not speculation or extrapolation. It is the direct consequence of measured oxygen consumption rates, experimentally determined thresholds for hypoxic brain injury, documented limits of cardiac function without oxygen, and decades of medical research on resuscitation and neurological outcomes. But vacuum exposure involves more than just oxygen depletion. There are additional physiological stresses that develop in parallel, and understanding them requires examining what happens to water and dissolved gases in body tissues when external pressure vanishes. Water boils when its vapor pressure exceeds the surrounding atmospheric pressure. This is a fundamental phase transition governed by thermodynamics. At 1 atmosphere of pressure, water boils at 100 degrees Celsius. At 0.5 atmospheres, roughly the pressure at 5,500 meters altitude, water boils at about 83 degrees Celsius. At 0.06 atmospheres, the pressure at the summit of Mount Everest, water boils at approximately 70 degrees Celsius. At the pressure of space, which is effectively zero, water boils at its triple point temperature, 0.01 degrees Celsius, or essentially at any temperature above freezing. At body temperature of 37 degrees Celsius, water's vapor pressure is about 47 millimeters of mercury, or roughly 0.062 atmospheres. In vacuum, this is far above the external pressure, so water spontaneously vaporizes. When a human body is exposed to vacuum, water on exposed surfaces, inside the mouth, on the tongue, in the nasal passages, on the surface of the eyes, and in the respiratory tract, begins to evaporate rapidly. This isn't a slow process. The evaporation rate in vacuum is limited only by the rate at which heat can be supplied to provide the latent heat of vaporization, which for water is about 2,260 joules per gram. This causes immediate cooling of those surfaces due to evaporative heat loss, a phenomenon familiar from sweating but occurring at an accelerated rate. The 1965 vacuum chamber survivor described the sensation explicitly. He felt the saliva on his tongue begin to boil. He reported it as a bubbling or fizzing sensation, not painful, but distinctly unusual and immediately recognizable. Tears on the surface of the eyes would similarly evaporate, causing rapid drying of the cornea. Moisture in the mouth and throat evaporates, leaving tissues desiccated. The lining of the lungs, normally kept moist to facilitate gas exchange, dries out within seconds. Critically, this boiling is confined to free surfaces where water is exposed directly to vacuum. Water inside cells and within blood vessels does not instantly boil because it's contained within tissue that provides structural resistance, and because the circulation distributes pressure somewhat through the hydrostatic pressure of the blood itself. Blood vessels maintain several millimeters of mercury pressure even without external atmospheric pressure, due to cardiac output and vascular tone. This internal pressure isn't sufficient to prevent all vaporization effects, but it does slow them. However, dissolved gases in the blood, primarily nitrogen, do come out of solution when external pressure drops. This is the same mechanism that causes decompression sickness, commonly called the bends, in divers who ascend too rapidly. Nitrogen is roughly 78% of atmospheric air, and it dissolves in body tissues and blood at a rate proportional to the partial pressure of nitrogen in the lungs. At sea level, tissues are saturated with nitrogen at 1 atmosphere of pressure. When external pressure suddenly drops to zero, that dissolved nitrogen becomes supersaturated. The tissues contain more dissolved gas than the new pressure can support, and the excess comes out of solution as bubbles. Nitrogen bubble formation in blood and tissues causes several problems. Bubbles in the bloodstream can block small vessels, reducing blood flow to tissues. This is particularly dangerous in the brain and spinal cord, where blocked vessels cause neurological symptoms ranging from confusion to paralysis. Bubbles in joints cause pain, the classic symptom of decompression sickness. Bubbles in the lungs can block pulmonary capillaries, reducing gas exchange and potentially causing right heart failure. The rate and severity of bubble formation depend on how much nitrogen is dissolved in tissues, which in turn depends on prior pressure exposure and duration. For a person at normal atmospheric pressure suddenly exposed to vacuum, significant bubble formation is expected. Animal studies in vacuum chambers have consistently shown evidence of gas bubble formation in blood samples taken after decompression. However, the timescale for severe tissue damage from nitrogen emboli is longer than the timescale for hypoxic brain damage. In other words, you lose consciousness from lack of oxygen before nitrogen bubbles cause major neurological harm. The bubbles form and begin causing damage, but the critical hypoxia threshold is reached first. Decompression sickness symptoms, when they occur, typically develop over minutes to hours after pressure reduction, not seconds. In vacuum exposure, if repressurization occurs within 2 minutes, before irreversible hypoxic damage, the nitrogen bubble formation is likely to be limited and potentially treatable with recompression therapy. If exposure extends beyond 5 minutes, the hypoxic damage dominates, and decompression sickness becomes a secondary concern. There is also significant fluid shift and swelling in vacuum. Exposed skin does not immediately freeze, contrary to popular depiction, but it does lose moisture rapidly through evaporation. The outer layers of the epidermis may swell slightly due to the reduction in external pressure, a condition called ebulism, where water vapor forms in tissue spaces, particularly in poorly perfused areas like the skin and subcutaneous tissues. This swelling has been observed in animal tests exposed to vacuum, and is consistent with known properties of tissue hydration and pressure balance. Ebulism causes tissue swelling to approximately twice normal volume in experiments with animals exposed to vacuum for several minutes. The skin becomes puffy and discolored, and subdermal blood vessels may rupture due to the pressure differential, causing bruising. However, this swelling develops over tens of seconds to minutes, not instantly, and like nitrogen bubble formation, it is not the immediate limiting factor for survival. The swelling is uncomfortable and potentially dangerous if prolonged, but it doesn't cause death in the first few minutes. The eyes are particularly vulnerable. The cornea and conjunctiva are delicate mucous membranes with high water content. In vacuum, the moisture evaporates almost instantly, and the intraocular pressure, normally about 15 to 20 millimeters of mercury, causes the eye to bulge slightly against the now absent external pressure. The cornea dries and may develop surface damage. Vision becomes blurred and then fails as corneal transparency is lost. However, this occurs in the context of a person already losing consciousness from hypoxia, so the visual effects, while dramatic, are not independently lethal. One often asked question is whether the eyes would pop or explode in vacuum. The answer is no. The structural integrity of the eye is sufficient to contain intraocular pressure even against vacuum. The sclera, the white outer layer of the eye, is a tough connective tissue capable of withstanding the pressure differential. Animal studies have not shown eye rupture in vacuum exposure. The eyes bulge and dry out, but they remain structurally intact. Now consider temperature, the second major constraint, and one where the physics is less intuitive. Space is often described as extremely cold, and this is true in one sense. The background temperature of space far from stars is approximately 2.7 Kelvin, or about minus 270 degrees Celsius. This is the temperature of the cosmic microwave background radiation, the afterglow of the Big Bang, which permeates all of space. However, temperature in the context of vacuum is not straightforward, because heat transfer requires a medium or mechanism. On Earth, heat is lost through three mechanisms: conduction to surrounding matter, convection as fluid moves, and radiation of electromagnetic energy. In space, there is no air or other matter to conduct heat to, and there is no convection because there is no fluid medium. The only remaining mechanism is radiation. The human body generates heat continuously through metabolism. At rest, an average adult produces approximately 100 watts of thermal power, equivalent to a standard incandescent light bulb. This heat is generated primarily by the liver, brain, heart, and skeletal muscles during basal metabolism. During physical activity, heat production increases dramatically. Intense exercise can produce 1000 watts or more. This metabolic heat must be dissipated to prevent hyperthermia, and under normal Earth conditions, the body uses sweating and vasodilation to dump excess heat into the environment. In vacuum, sweating is ineffective because the evaporated water is lost to space and provides no cooling regulation. It simply continues evaporating until the surface is dry. Conduction and convection are absent. The only path for heat loss is thermal radiation, and the rate of radiative heat transfer is determined by the Stefan-Boltzmann law P equals epsilon sigma, Tt, where P is radiated power, epsilon is emissivity, sigma is the Stefan-Boltzmann constant, A is surface area, T is body temperature, and T is the temperature of the surroundings. For human skin, emissivity is approximately 0.98, meaning it radiates almost as efficiently as a perfect blackbody. The surface area of an average adult is about 1.7 to 1.8 square meters. At normal body temperature of 310 Kelvin, 37 degrees Celsius, and assuming the surrounding environment is at near absolute zero, the body radiates approximately 900 to 1000 watts of thermal energy. This immediately presents an apparent problem. The body generates 100 watts but radiates 900 watts, creating a net heat deficit of 800 watts. This sounds catastrophic, as if the body would cool almost instantly. However, this calculation is misleading because it assumes the entire body is at uniform temperature and all parts are radiating at full efficiency. In reality, the body is not isothermal. Only the skin's surface radiates efficiently, and the rate of heat loss is limited by how quickly heat can be conducted from the body's core, the interior organs and tissues, to the skin's surface. Human tissue is a poor conductor of heat. Thermal conductivity is approximately 0.5 watts per meter per Kelvin for muscle and about 0.2 watts per meter per Kelvin for fat. This is similar to water and far lower than metals. The thermal resistance of the body means that heat flows slowly from the core to the surface. As the skin cools through radiation, a temperature gradient develops, with the core remaining warmer than the skin. The core continues to generate metabolic heat, and this heat slowly diffuses outward through tissue layers. Calculations based on thermal models of the human body, validated against experimental data from cold exposure studies, indicate that core body temperature would drop at a rate of roughly 1 degree Celsius every 10 to 15 minutes in vacuum conditions without any external heat source. This assumes a resting metabolic rate and typical body composition. A person with more body fat, which provides insulation, would cool more slowly. A lean person with less subcutaneous fat would cool faster. Hypothermia is medically defined as core body temperature below 35 degrees Celsius. At this temperature, cognitive function becomes impaired, motor coordination deteriorates, and the person experiences confusion and slowed reactions. From a normal core temperature of 37 degrees Celsius, reaching 35 degrees would take approximately 20 to 30 minutes in vacuum, based on the calculated cooling rate. Mild hypothermia, between 32 and 35 degrees Celsius, is survivable and potentially reversible with rewarming. Moderate hypothermia, between 28 and 32 degrees, causes progressive loss of consciousness, cardiac arrhythmias, and decreased respiratory rate. Severe hypothermia, below 28 degrees Celsius, results in cardiac arrest, cessation of brain activity, and apparent death, although successful resuscitation from severe hypothermia has been documented in cases where victims were rapidly rewarmed. Reaching 28 degrees Celsius from normal body temperature in vacuum would take roughly 2 to 3 hours based on thermal modeling. This is far longer than the 10-minute hypoxia limit we established earlier. Therefore, thermal loss, while real and eventually lethal, is not the limiting factor for short-term survival in vacuum. A person would lose consciousness from hypoxia in 15 seconds, suffer irreversible brain damage in 2 to 5 minutes, and die from oxygen deprivation and cardiac arrest in 5 to 10 minutes, long before hypothermia becomes the primary cause of death. However, this conclusion changes if we modify the scenario. Suppose a person has a functioning oxygen mask supplying pressurized gas to breathe, allowing them to maintain consciousness and oxygen delivery, but their body is otherwise exposed to vacuum. In this scenario, the hypoxia constraint is removed, and thermal loss becomes the relevant limiting factor. With oxygen supplied but no insulation or active heating, the person would experience progressive hypothermia. Consciousness would remain for 30 minutes or more as body temperature slowly dropped. At 45 minutes to an hour, moderate hypothermia would set in, causing confusion and impaired judgment. At 90 minutes to 2 hours, severe hypothermia would cause loss of consciousness. At 3 to 4 hours, cardiac arrest from hypothermia would occur. This scenario is essentially equivalent to cold water immersion, where the thermal conductivity of water rapidly draws heat from the body. In vacuum, the cooling is slower due to the poor conductivity of the radiative heat transfer mechanism, so survival time is somewhat longer than in cold water, but the outcome is the same. This scenario is not purely hypothetical. Spacesuits are designed precisely to address this problem. A spacesuit maintains internal pressure, supplies oxygen, and crucially includes active thermal regulation systems, either water-cooled garments that circulate temperature-controlled liquid through tubes next to the skin, or heating elements powered by the suit's electrical system. Without active thermal control, an astronaut in a spacesuit would overheat due to metabolic heat and solar radiation rather than freeze, which is why cooling systems are a critical component of suit design. The thermal environment also depends strongly on whether the body is in sunlight or shadow. In near-Earth space, solar radiation delivers approximately 1,367 watts per square meter on a surface perpendicular to the Sun, a value called the solar constant. For a human body oriented toward the Sun, perhaps 0.5 square meters of surface area would be directly illuminated, receiving about 680 watts of solar energy. This incoming energy offsets radiative heat loss, potentially even creating a net positive heat balance on the illuminated side while the shadowed side continues to lose heat. This asymmetric heating would create extreme temperature gradients across the body. The side facing the Sun could reach temperatures above 100 degrees Celsius, while the side facing away could drop below freezing. Animal experiments with exposure to simulated space conditions have demonstrated this effect, with surface temperature differences exceeding 100 degrees Celsius between sunlit and shadowed areas of the same subject. In direct sunlight, without the ability to radiate heat efficiently away from the illuminated surface, portions of the body could experience thermal burns and tissue damage from overheating within minutes to tens of minutes. However, this is localized surface damage, not core hyperthermia. The core body temperature would rise more slowly, perhaps reaching dangerous levels above 40 degrees Celsius after 1 to 2 hours of continuous sun exposure. Hyperthermia severe enough to cause heat stroke and loss of consciousness occurs at core temperatures above 40 to 42 degrees Celsius, and tissue damage accelerates above 43 degrees, where proteins begin to denature. So the thermal situation in space is complex and depends critically on exposure to sunlight. In shadow, hypothermia is the thermal threat, developing over hours. In sunlight, localized overheating and eventually hyperthermia become concerns, also over a timescale of hours. Neither thermal extreme operates on the timescale of seconds to minutes that governs hypoxia, so for unprotected vacuum exposure, thermal effects remain secondary to oxygen deprivation. Next is radiation, the third major environmental constraint and the one most often misunderstood or exaggerated. Space beyond Earth's protective magnetosphere is filled with ionizing radiation from multiple sources. The solar wind consists primarily of protons and electrons streaming outward from the Sun at velocities of 300 to 800 kilometers per second. Galactic cosmic rays are high-energy particles, predominantly protons but including heavier nuclei up to iron and beyond, originating from supernovae and other energetic events in the galaxy. Solar particle events occur intermittently when the Sun releases bursts of high-energy protons during solar flares and coronal mass ejections. Each of these radiation sources has been measured extensively by space probes, satellites, and instruments aboard the International Space Station and other spacecraft. The dose rate from galactic cosmic rays in deep space, far from Earth and outside any shielding, is approximately 0.5 to 1 millisievert per day, based on measurements from instruments aboard the Voyager probes, the Mars Science Laboratory during its cruise to Mars, and calculations from particle physics models. This dose rate varies with the solar cycle. Cosmic ray intensity is highest during solar minimum when the Sun's magnetic field is weakest and provides less deflection of incoming particles. A millisievert is a unit of equivalent dose, which accounts for both the energy deposited by radiation and the biological effectiveness of different radiation types. For context, a typical chest X-ray delivers about 0.1 millisieverts. A CT scan of the abdomen delivers roughly 10 millisieverts. Annual background radiation on Earth from natural sources averages about 2 to 3 millisieverts, though this varies with altitude and local geology. Acute radiation sickness begins at whole-body doses above approximately 1,000 millisieverts, or 1 sievert, delivered over a short period, typically hours to days. Symptoms include nausea, vomiting, fatigue, and temporary reduction in blood cell counts. These effects are reversible, and most people recover fully. At doses around 3 to 4 sieverts, about half of exposed individuals would die within 60 days without medical treatment due to bone marrow failure and infection. At 5 to 6 sieverts, survival becomes unlikely even with medical intervention. Above 10 sieverts, survival is effectively impossible. Damage to the gastrointestinal tract and central nervous system is so severe that death occurs within days to weeks. At the measured deep space dose rate of 0.5 to 1 millisievert per day, accumulating a dose of 1 sievert, the threshold for acute radiation sickness, would require 1,000 to 2,000 days, or roughly 3 to 5.5 years. This is clearly far too slow to be relevant for short-term survival. Even accumulating a dose sufficient to cause any immediate symptoms would take months to years. Radiation, therefore, is not a limiting factor for survival on the timescale of minutes, hours, or even days in deep space. It becomes relevant only for extended missions measured in months or years, where cumulative dose increases long-term cancer risk and may cause cataracts, cardiovascular effects, and damage to the central nervous system. For the question of maximum survival time during immediate vacuum exposure, radiation is negligible compared to hypoxia, decompression effects, and thermal stress. However, one radiation scenario warrants examination: exposure during a solar particle event. Solar flares can release enormous bursts of protons with energies ranging from a few million electron volts to over 1 billion electron volts. These particles, traveling at significant fractions of the speed of light, reach Earth's orbit within minutes to hours after a flare. The intensity varies enormously between events, but the largest recorded events provide a measured upper bound on the danger. The August 1972 solar particle event, one of the most intense on record, occurred between the Apollo 16 and Apollo 17 missions. Had astronauts been on the lunar surface during that event without shielding, they would have received doses estimated at 5 to 10 millisieverts per hour during the peak intensity, based on particle flux measurements from satellites and modeling of radiation transport through tissue. An unprotected person exposed for 1 hour would receive 5 to 10 millisieverts, enough to measurably increase long-term cancer risk but far below the threshold for acute symptoms. Exposure for a full day during such an event might deliver 100 to 200 millisieverts, still below the threshold for acute radiation sickness but representing a significant dose equivalent to dozens of chest X-rays. The exposed individual would experience no immediate symptoms, but would face substantially increased cancer risk years later. Crucially, this dose would not cause unconsciousness, cognitive impairment, or any immediate physiological effect that would contribute to short-term survival limits. Even during the most extreme solar particle events observed, the dose rates do not approach immediately lethal levels on timescales of hours to days. The most intense event in recorded history, the Carrington event of 1859, likely produced higher particle fluxes than the 1972 event, but even conservative estimates of radiation dose suggest survivable levels for exposures of hours to days, though with serious long-term health consequences. Therefore, while radiation is a genuine hazard for extended space missions and must be carefully managed through shielding and mission planning, it does not affect the maximum survival time for unprotected vacuum exposure. The 10-minute survival limit established by hypoxia remains the governing constraint. Having established the primary limits, hypoxia, pressure effects, and thermal stress, let's examine what happens to the body after death in space, because this completes our understanding of the biological boundaries we've been discussing. A body in space does not decay in the manner familiar on Earth. Decomposition is driven by bacteria, fungi, and insects, all of which require oxygen, moisture, and moderate temperatures to function. In the vacuum of space, there is no oxygen to support aerobic bacteria, and the extreme conditions, either freezing in shadow or alternating between hot and cold in sunlight, are outside the viable range for most microorganisms. The body cannot rot in the conventional sense. Instead, the body undergoes mummification. Water evaporates from exposed surfaces and gradually from deeper tissues over time, driven by the vacuum environment. This desiccation process slowly removes moisture, leaving tissues dried and preserved. In shadow, the body remains cold, and any remaining water may freeze, forming ice crystals that further preserve structure. The process is similar to freeze-drying, a technique used in food preservation where material is frozen and then exposed to vacuum to remove water by sublimation. In sunlight, the situation is more complex. The illuminated surfaces heat up, potentially above the freezing point of water, allowing liquid water to evaporate rather than sublimate from ice. The shadowed surfaces remain frozen. Over cycles of solar exposure, if the body is tumbling or orbiting such that different surfaces alternately face the sun, the desiccation proceeds unevenly, but the end result is the same: a dried, preserved body with structural integrity maintained but all biological function permanently ceased. Radiation gradually damages cellular structures over time. High-energy particles break chemical bonds in DNA, proteins, and lipids. This degradation is cumulative and irreversible. Over months and years, the body becomes increasingly discolored as complex organic molecules break down into simpler compounds. Surface tissues may darken from radiation damage. However, the bulk structure remains preserved because the desiccation has essentially halted all biological processes, including decay. This mummification process has implications for any theoretical recovery scenario. A body that has been in space for weeks or months would be recognizable, structurally intact, and preserved well enough for identification, though extensively damaged at the molecular level. This contrasts sharply with terrestrial decomposition, where a body exposed to air and microorganisms can become unrecognizable within weeks. There is also the question of micrometeoroid impacts. Space is not truly empty. It contains dust particles, small rocky fragments, and in near-Earth orbit, debris from satellites and spacecraft. A body in space would eventually be struck by micrometeoroids, though the probability of impact depends on location and time. In deep space, far from Earth's debris cloud, micrometeoroid flux is approximately 1 particle larger than 1 microgram per square meter per second, based on measurements from long-duration spacecraft. For a human body with surface area of about 2 square meters, this translates to roughly 1 small particle strike every few days to weeks for particles large enough to cause visible damage. Over months and years, these impacts would accumulate, creating small pits and craters on the surface. Over centuries, the cumulative damage from countless small impacts would gradually erode the body, but on any timescale relevant to human missions or recovery operations, micrometeoroid damage would be minimal. Gravitational and orbital dynamics also determine the long-term fate of a body in space. A body does not simply float stationary where it's released. It follows an orbit determined by its initial velocity and the gravitational influence of nearby bodies. In low Earth orbit, atmospheric drag, though extremely weak at altitudes above 200 kilometers, eventually causes orbit decay. The time to re-entry depends on altitude. At 300 kilometers, re-entry occurs within months to a few years. At 400 kilometers, the altitude of the International Space Station, re-entry takes several years to a decade. During re-entry, the body would be heated to thousands of degrees by friction with the thickening atmosphere and would be completely vaporized, leaving no trace. In higher orbits or in deep space trajectories, the body could remain in orbit for thousands or millions of years, gradually perturbed by gravitational interactions with the Moon, planets, and eventually by the solar wind and radiation pressure. In truly deep space, far from the Sun and planets, the body would continue along its trajectory indefinitely, eventually perhaps perturbed by gravitational interactions with passing stars over hundreds of thousands to millions of years. All of this extends far beyond any timescale relevant to survival, but it completes the picture of what space does to biological material and reinforces the permanence of the physiological limits we've discussed. Let's now consider the human factors and psychological dimensions of the survival timeline, because these provide context for how the limits we've established translate into lived experience, however brief that experience may be. The 15 seconds of consciousness before hypoxic blackout is not a long time, but it is long enough for a person to be aware of what is happening. The survivor of the 1965 vacuum chamber incident reported a clear sequence of sensations and awareness. He felt the pressure drop immediately, a sensation of air rushing out of his lungs. He experienced the peculiar feeling of saliva boiling on his tongue, which he described as bubbling or fizzing, not painful, but strange and alarming. He remained aware and attempted to reach the repressurization controls, but before he could complete the action, his vision began to narrow and darken from the periphery inward, a classic symptom of cerebral hypoxia. Then he lost consciousness. The entire sequence from decompression to blackout took approximately 14 seconds. His account, the only first-hand description we have of near-vacuum exposure, reveals that the experience is not one of immediate panic or pain. The sensations are unusual and alarming, certainly, but not agonizing. The rapidity of unconsciousness means that fear and suffering are brief. This is consistent with accounts from high-altitude aviators who have experienced rapid decompression at extreme altitude, and from medical studies of hypoxia where subjects describe a dreamlike fading of awareness rather than acute distress. The psychological experience, then, is mercifully short. Panic might occur in the first few seconds as the person realizes what is happening, but cognitive function deteriorates too quickly for sustained terror. This is not to minimize the tragedy of such an event, but rather to acknowledge that the physiological timeline imposes limits on suffering as well as on survival. Within 15 seconds, the person is unconscious and unaware. They do not experience the subsequent minutes of hypoxic brain damage or the eventual cardiac arrest. The subjective experience ends quickly. For astronauts and mission planners, this knowledge informs training, procedures, and spacecraft design. Spacesuits are engineered with multiple redundancies to maintain pressure. The outer layer, called the thermal micrometeoroid garment, protects against debris and provides thermal insulation. Beneath it, the pressure bladder maintains air pressure, typically 4.3 pounds per square inch for NASA's extravehicular mobility unit, about 0.3 atmospheres, a compromise between safety and suit flexibility. Multiple layers of redundancy ensure that a single puncture or tear does not cause catastrophic pressure loss. If a suit breach occurs, astronauts are trained to respond immediately. Small leaks can sometimes be temporarily sealed with patches or by covering the breach with a gloved hand. Larger breaches may require immediate return to the airlock and repressurization. The suit's life support systems include warnings for pressure loss, and protocols exist for rapid emergency procedures. The goal is to ensure that the timeline we've discussed, 15 seconds to unconsciousness, 2 minutes to irreversible damage, is never reached. That intervention always occurs in the first few seconds of any pressure loss. There have been close calls in the history of spaceflight that illustrate these narrow margins. In 1982, Soviet cosmonaut Valentin Lebedev experienced a spacesuit leak during a spacewalk outside the Salyut 7 space station. The suit pressure dropped measurably but not catastrophically, and he reported feeling mild discomfort and hearing loss as the pressure decreased. He was able to return to the airlock and repressurize before the situation became life-threatening. Post-mission analysis revealed a small tear in the suit's outer layers that had allowed slow pressure loss. Had the tear been larger or had return been delayed, the outcome could have been fatal. In 2013, Italian astronaut Luca Parmitano experienced a different, but equally dangerous malfunction during a spacewalk outside the International Space Station. His helmet began filling with water due to a contamination issue in the suit's cooling system. Water accumulated in the helmet, covering his ears, then his eyes, and eventually beginning to block his nose and mouth. He was in immediate danger of drowning inside the suit, despite being surrounded by pressurized oxygen. The spacewalk was terminated, and he returned to the airlock, but the incident revealed how small malfunctions can create life-threatening scenarios even within a functioning spacesuit. Had he been unable to return quickly, he would have drowned within minutes, an outcome as fatal as vacuum exposure, though through a different mechanism. These incidents underscore the critical importance of suit integrity and the narrow margins between safety and disaster in the space environment. They also highlight the professionalism and training of astronauts, who are prepared to respond calmly and effectively even in life-threatening emergencies. The engineering that goes into spacesuits reflects every physiological limit we've discussed. Pressure must be maintained within a narrow range. Too low and hypoxia occurs, too high and mobility becomes impossible. Oxygen concentration and flow rate must be sufficient to maintain normal blood oxygen saturation, typically achieved by providing pure oxygen at the suit's reduced pressure. Thermoregulation systems must remove metabolic heat and protect against the thermal extremes of space. Every component is designed around measured human tolerances. The difference between near-Earth space and deep space operations also matters significantly for risk and survival. In low Earth orbit, the International Space Station is always within communication range of ground control. An emergency return to Earth via Soyuz or other spacecraft is possible within hours. If a catastrophic failure occurs, rescue might be feasible within a very compressed timeline, though still constrained by orbital mechanics and available resources. In deep space missions, beyond the Moon, en route to Mars, or on missions to asteroids or the outer solar system, there is no rapid rescue capability. The nearest help is months or years away. If a suit fails or a spacecraft depressurizes, the crew must rely entirely on their own equipment, training, and resourcefulness. The survival timelines are identical to those we've discussed, but the consequences of failure are absolute because no external help can arrive in time. This has profound implications for mission design. Deep space missions require extreme redundancy in life support systems, robust repair capabilities, and rigorous testing of all equipment. Risk assessments must account for scenarios where rescue is impossible. Crew selection emphasizes not only technical skills but psychological resilience, because the knowledge that help is not available creates a different kind of pressure. One question often raised is whether survival time could be extended through physiological preconditioning or adaptation. Could training, medication, or other interventions push the limits beyond what we've established? Pre-breathing pure oxygen before spacewalks is standard practice for astronauts. This serves two purposes. It increases oxygen saturation in tissues, and it reduces dissolved nitrogen, minimizing the risk of decompression sickness when transitioning from the spacecraft's atmosphere to the lower pressure of the spacesuit. However, the effect on oxygen reserves is modest. Hemoglobin is already 97 to 99% saturated under normal air breathing, so switching to pure oxygen increases saturation only marginally, perhaps from 97% to 100%. This represents a small increase in total oxygen reserve, perhaps extending consciousness by an additional 2 to 3 seconds, but not enough to fundamentally change the survival timeline. Could hypothermia be induced intentionally to slow metabolism and extend survival? Reduced metabolism would decrease oxygen consumption, potentially prolonging the time before critical oxygen depletion. This principle is used in medicine. Therapeutic hypothermia is employed during cardiac surgery to protect the brain during periods of reduced circulation. Cooling a patient to 28 to 32 degrees Celsius can reduce cerebral oxygen consumption by 50% or more, allowing the brain to tolerate longer periods without full blood flow. However, inducing hypothermia requires time, controlled cooling, and stable conditions, none of which are available during sudden vacuum exposure. In clinical settings, achieving therapeutic hypothermia takes 30 minutes to several hours using cooling blankets, intravenous cold saline, or external cooling devices. The body cools in vacuum, as we've discussed, but the rate is too slow to reduce core temperature significantly within the critical first minutes when hypoxia occurs. By the time cooling has progressed enough to substantially reduce metabolism, the person is already unconscious and suffering hypoxic brain damage. What about training to tolerate hypoxia? High-altitude mountaineers who acclimatize to extreme elevations develop physiological adaptations over weeks. Increased red blood cell production driven by erythropoietin, improved oxygen extraction efficiency in muscles, and increased capillary density in tissues. Freedivers train to extend breath hold duration, achieving times of 5, 7, or even 10 minutes in exceptional cases. These adaptations genuinely improve performance in their specific contexts. A well-acclimatized mountaineer can function at altitudes where an untrained person would quickly lose consciousness. A trained freediver can tolerate much longer periods without breathing than an untrained individual. However, these adaptations do not fundamentally change the brain's oxygen requirements or its vulnerability to acute hypoxia. They allow for more efficient use of available oxygen and better tolerance of elevated carbon dioxide, but they cannot eliminate the brain's absolute dependence on continuous oxygen delivery. In the specific scenario of vacuum exposure, where breathing has stopped and no new oxygen is entering the system, the increased red blood cell count of an acclimatized mountaineer provides only a marginal benefit, perhaps a few extra seconds of consciousness due to slightly higher oxygen carrying capacity. The freediver's training in breath holding is irrelevant because breath holding requires starting with full lungs and managing carbon dioxide buildup, either of which is possible during vacuum exposure where the lungs are empty and decompression is complete. A trained individual might remain conscious 1 or 2 seconds longer than an untrained person, but the difference is minimal. The physiological limits we've described are set by fundamental biochemistry. Neurons require ADP, ADP requires oxygen, and oxygen delivery requires breathing and circulation. When those systems fail, no amount of training can prevent the cascade toward unconsciousness and death. The human body, despite its remarkable adaptability to diverse environments on Earth, is ultimately constrained by the requirements of cellular metabolism. Every cell in the body requires continuous energy supply in the form of ADP. ADP is produced primarily through oxidative phosphorylation in mitochondria, a process that absolutely requires oxygen. When oxygen is absent, cells switch to anaerobic glycolysis, which produces only a tiny fraction of the ADP that oxidative metabolism produces, roughly 5% as much per glucose molecule. This is sufficient for tissues like muscle during brief intense effort, but it is not sufficient for the brain. Brain tissue cannot store energy reserves the way muscle stores glycogen or fat tissue stores lipids. The brain must rely on immediate glucose and oxygen delivery from the bloodstream. When either is interrupted, function ceases within seconds to minutes. This is not a design flaw or a vulnerability that could be engineered away through training or adaptation. It is a fundamental consequence of the energy demands of neurocomputation. Maintaining electrical potentials across billions of neurons, synthesizing and recycling neurotransmitters, and powering the molecular machinery of synapses requires enormous amounts of energy, and that energy must come from oxidative metabolism. This brings us to a final consideration: what these limits tell us about human space exploration and the conditions necessary to sustain life beyond Earth. The 10-minute maximum survival time in unprotected vacuum is not just a physiological curiosity. It defines the absolute requirement for life support in any space environment. There is no gradual adaptation, no slow acclimatization that could allow humans to tolerate vacuum the way we can adapt to high altitude or cold. The transition from normal pressure to vacuum is a binary threshold: either protective equipment maintains livable conditions, or death occurs within minutes. Every human mission beyond Earth's atmosphere is therefore fundamentally an exercise in carrying a piece of Earth with us. Spacecraft maintain 1 atmosphere of pressure, 20 to 21% oxygen, controlled temperature, and radiation shielding. Space stations provide larger habitable volumes, but with the same basic requirements. Spacesuits are miniaturized life support systems worn on the body. In all cases, we create a narrow envelope of conditions that match Earth's surface because those are the only conditions under which human physiology can function. The engineering requirements are stringent. Pressure vessels must withstand the differential between internal atmosphere and external vacuum without leaking. Life support systems must continuously supply oxygen, remove carbon dioxide, control humidity, and regulate temperature. Radiation shielding must reduce dose rates to tolerable levels for long-duration missions. Every system must have redundancy because a single failure can be immediately fatal. The 10-minute survival limit provides no margin for error, no time to jury-rig repairs or await rescue. This is why space exploration remains difficult and expensive despite decades of technology development. The challenges are not primarily about propulsion or navigation. Those are solvable engineering problems. The fundamental challenge is maintaining a habitable environment for fragile biological organisms in an environment hostile to life. Every kilogram of life support equipment is a kilogram that could have been payload or fuel. Every redundant system adds complexity and points of failure. Yet all of it is necessary because the physiological limits permit no compromise. The 10-minute survival limit also illuminates the narrow range of conditions compatible with life in general. We think of Earth as the norm, the baseline, but in the context of the cosmos, Earth's surface represents an extreme outlier. Most of the universe is vacuum, or near vacuum. Most of it is at temperatures near absolute zero or, near stars, at temperatures that vaporize rock. Most of it is bathed in radiation that would be immediately lethal to unshielded organisms. The conditions we require, liquid water, moderate temperature, atmospheric pressure, protection from radiation, exist naturally in only a tiny fraction of cosmic environments. Life on Earth persists because a specific set of conditions happens to align here. A planet with sufficient mass to retain an atmosphere, positioned at a distance from its star where temperatures allow liquid water, protected by a magnetic field that deflects solar wind, with an atmosphere that filters harmful radiation while admitting visible light. These conditions arose through planetary formation processes and have been maintained, with fluctuations, for billions of years. When we step outside that narrow envelope, we step outside the conditions life requires, and our bodies respond according to fixed physiological limits. The cascade is predictable. Pressure loss leads to inability to breathe. Oxygen depletion causes unconsciousness within 15 seconds, brain damage begins at 2 minutes, and death is certain within 10 minutes. These are not estimates or approximations. They are measured consequences of how human biology operates at the cellular level. The specificity of these numbers, 15 seconds, 2 minutes, 10 minutes, reflects the precision with which biological systems are tuned to Earth's conditions. A neuron maintains a resting potential of -70 millivolts. An ion pump requires 7 kilocalories per mole to transport sodium against its concentration gradient. Hemoglobin changes its oxygen affinity based on pH shifts of 0.1 units. These are not round numbers or convenient approximations. They are the exact values measured in laboratories and confirmed across millions of experimental observations. When the environment changes beyond the range these systems can accommodate, failure occurs on timescales directly calculable from the underlying biochemistry. Understanding these limits doesn't diminish the achievement of space exploration, it enhances it. Every astronaut who has walked in space, every crew that has lived aboard a space station, every mission to the Moon or Mars has succeeded by meticulously maintaining the conditions required for human survival within a vessel or suit, surrounded by an environment that would kill in minutes. The engineering precision required is extraordinary, and the margin for error is vanishingly small. The limits also define what is possible for future exploration. Missions to Mars, the outer solar system, or eventually to other stars must provide continuous life support for months or years. The spacecraft become miniature worlds, self-contained ecosystems maintaining pressure, atmosphere, temperature, food, water, and radiation protection. The longer the mission, the more reliable these systems must be, because the 10-minute survival limit means that catastrophic failure is immediately fatal with no possibility of rescue. Some have proposed concepts for hibernation or suspended animation to reduce life support requirements during long transits. If human metabolism could be slowed dramatically through induced hypothermia or other means, oxygen consumption would decrease, and the duration a person could survive on limited resources would extend. However, current medical technology cannot safely maintain suspended animation for more than a few days, and the risks of complications, blood clots, infection, organ damage, increase with duration. No near-term technology can extend this to the months or years needed for interplanetary travel, and even if such technology were developed, the crew would still need to be revived periodically, at which point full life support would be required. The physiological limits we've examined are therefore not just constraints on survival and vacuum but fundamental boundaries that shape what kinds of space missions are feasible, and what kinds remain beyond our current capabilities. They define the minimum requirements for any habitat, any suit, any mission architecture. They cannot be negotiated or compromised because they are rooted in biochemistry that has been stable for hundreds of millions of years of evolution. In conclusion, the maximum time a human can survive in deep space, unprotected, is approximately 10 minutes. This figure is determined by the rate of oxygen depletion in the bloodstream, the tolerance of brain tissue to hypoxia, and the time required for irreversible cellular damage to occur. Consciousness is lost within 9 to 15 seconds due to oxygen depletion. Brain damage begins at 2 minutes as neurons exhaust their energy reserves and begin dying. By 5 minutes, the damage is extensive and likely irreversible. At 10 minutes, cardiac arrest occurs, and resuscitation becomes impossible. These timelines are not speculative. They are derived from documented incidents of vacuum exposure, controlled studies with animal subjects, medical research on hypoxia and resuscitation, and measurements of human metabolic rates and oxygen consumption. Every element of the timeline is constrained by physical laws: Boyle's law for gas expansion, the Stefan-Boltzmann law for radiative heat transfer, the phase diagram of water for vapor pressure, and biological limits measured in laboratories and confirmed in clinical practice. Additional factors: decompression sickness from nitrogen bubble formation, embolism from tissue swelling, thermal stress from radiative heat loss, and radiation exposure, all occur during vacuum exposure but operate on longer timescales. They contribute to the overall lethality of space but do not determine the maximum survival time because hypoxic brain damage occurs first and fastest. The 10-minute limit applies to scenarios where no protective equipment is present. With partial protection, such as a pressure suit that fails but retains some oxygen supply, survival time extends to hours, limited by thermal regulation. With full life support but in a hostile environment like deep space, survival becomes indefinite, constrained only by the reliability of equipment and resupply of consumables. These limits illuminate the fundamental challenge of human spaceflight. We are evolved for Earth's surface, and we cannot survive anywhere else without continuously maintaining the specific conditions our biology requires. The universe does not provide those conditions naturally beyond a few rare planetary surfaces. Space is vacuum because matter disperses without gravity to constrain it. It is cold because radiative equilibrium at interstellar distances approaches absolute zero. It is filled with radiation because stars and cosmic events produce high-energy particles that travel freely through empty space. None of this is hostile in any intentional sense. It is simply the default state of the cosmos. Life is the extraordinary exception, existing only where and when specific conditions align. When we venture beyond those conditions, our survival depends entirely on our ability to carry those conditions with us, contained in vessels of metal and fabric, maintained by machines and careful engineering. The 10-minute survival limit is the measure of how quickly we die when that artificial envelope fails. If you found this detailed examination of experimentally verified limits valuable, engaging with the video supports the creation of similar evidence-based content that prioritizes scientific rigor over sensationalism, helping it reach audiences who value accuracy and precision in science communication.